Hello, everyone, and welcome back. So in the previous video, we introduced derivatives. We did it. We got there. We got through integration, and now we're talking about derivatives. It feels like familiar territory again if we took a calculus class. And if you think back to an introductory calculus class, there are what I like to refer to as the big three theorems that you learn. Now, we've talked about two of them already, the extreme value theorem and the intermediate value theorem. So now you can try and rack your brain to remember what is the third one. Now, if you're looking at the title of this video, you know that it is the mean value theorem. And if you can remember the mean value theorem, you remember that it includes a derivative. We did it, right? We finally got to a point where we can introduce the third of the big three theorems. And so that's exactly what we're going to talk about today, the mean value theorem. Now, we are going to go through a number of subjects today. There's actually going to be a lot of definitions, most of which are just going to cement things that you probably already understand, again, if you already took an introductory calculus class. So we're going to talk about increasing and decreasing functions. And this is actually going to lead us to start talking about a very famous theorem called Rolle's theorem. And in fact, the mean value theorem can always just be thought of as a generalization of Rolle's theorem. Similarly, as we're going to see, just like in the previous lecture, there's a strong connection between the mean value theorem and Taylor's theorem. Okay, that's enough of an introduction. Let me go ahead and start us off with a nice definition of increasing and local maxima and local minima of a function. All right. So as promised, start with a definition. So we are going to say now this will be local maxima. So local maximum. And we might as well do it all at once. Local minimum too. Local minimum. Points of f defined below are called local extreme points. Okay, so then what is the actual local maximum and local minimum? Well, we're going to do this absent of the derivative, right? So we're going to talk about this in complete generality. So this would apply to just continuous functions as well as differentiable functions. So a function f is said to have a local maximum. I'm going to just write max. Maximum's a lot of words. It leaves a lot of room for me to misspell something. Local maximum point at a point A in the domain of f, if and only if there exists some delta greater than 0, such that if x is in my domain and within delta of the local maximum point A, this implies that f at that x value is less than or equal to f of A, right? So everything in a neighborhood of your maximum point A returns a value in f that's smaller than f of A, or smaller than or equal, of course. Well, you can probably take a wild guess at figuring out what a local minimum is, right? So a function fn, f is said to have, so it's more writing than thinking at this point, a local min point at, let's just use A again. It's easy, at A in the domain, if and only if there exists a delta. So it's basically going to be exactly the same statement. You're just going to reverse the inequality on your function. If this implies f of x is greater than or equal to f of a. So again, what this says is that if you have a local minimum point and you look around it, all of the values of f, the range of f in this neighborhood, well, the smallest value that's going to come out of there is f of a. Okay, so this is probably a little tedious, but what I really, really want to emphasize to you is that nothing includes the derivative here, right? Sometimes people think about local extrema as like where the derivative is equal to 0, and we're going to get to that. But for the time being, this doesn't rely on derivatives. All right, let me give you one more definition before we start having a little bit of fun here. So a point A is called an interior point. Of the domain D of f. Now, this is going to work actually for any set of real numbers, but in our context, what we really care about is domains. So if and only if there exists a delta greater than 0 such that you can wiggle around close to this point and still stay in the domain. And we say the set of all interior points of df is denoted by df with a little sort of degree symbol at the top. That's, in my opinion, that is an O, stands for open. There's a deep connection here to open sets. Technically, the interior is the largest open set that resides in your set. This is more of a topological definition, and so we're not going to delve too deep into this. I just want you to know what it means to be an interior point. And we call this the interior of D of f. Okay, so with this, the collection of all interior points is called the interior. Again, largest open set that resides in your set. Don't think too deeply on it. Basically, for our purposes, this is just points in the interior if you can wiggle around near it. So if there exists an open set, right? This is very, very closely related to open sets that we learned about way back at the beginning of the class. But now we can get that theorem that tells us the derivative is equal to 0 when we're at local extrema. So if f is differentiable, remember we introduced this definition. This is the same as having a derivative at a point at a local extreme point. And we're going to call it mu, and it's going to be assumed to belong to the interior. This is very, very important. Remember, the new thing that we've talked about extensively in this class is that functions have to come with the domain. And that means that all of our definitions and our theorems and our proofs have to intricately include the domain. So in this case, the only way this is going to work is if you're at an interior point, and then f prime of mu is equal to 0. So if you have a local extreme point in the interior of your domain, then the derivative is equal to 0. Okay, let me show you the proof, and this is why you need the interior point. So I'm going to break this into two cases. Let's assume f has a local max at mu. And again, this is in the interior of your function. Then there exists some delta greater than 0 such that, well, I can wiggle around near this interior point, and this still keeps me inside of the domain. And, well, let me, as you can see, I'm going to move down a page here. So when I take my h positive and smaller than delta, this implies, well, here I have f of mu plus h minus f of mu divided by, sorry, I put delta in there, that should be h, divided by h. Well, we know that f of mu is mu is a local maximum. So that means f of mu plus h is smaller than f of mu. So the top of this thing is negative. H is a positive value, means the whole quotient is less than or equal to 0. Whereas if negative delta is less than h, which is less than 0, so essentially thinking about the limit coming from the left, this implies, well, that quotient, again, the numerator is negative, but now I'm dividing by a negative number, tells me I'm greater than or equal to 0. But thus, again, now when we put these things in terms of limits, we get the limit as h goes to 0 of f of mu plus h minus f of mu divided by h. Well, the inequality passes to the limit, and you get the same thing as the limit as h goes to 0 from the left. Same thing, the inequality will pass to that limit. And so this is greater than or equal to 0. Pardon me for having to squeeze it in. But since f is actually differentiable, since this exists, we have that from the first inequality, this is less than or equal to 0. And from the second inequality, this thing is greater than or equal to 0, which means that f prime of mu is equal to 0 as desired, which shows that my derivative is equal to 0 at a local maximum. So in the second case, if f has a local minimum, we do this trick all the time. We're basically just going to multiply by a negative and repeat the first piece. So if f has a local minimum at mu, then g equal to minus f has a local max at mu, which from the first case implies g prime of mu is equal to 0, but also f prime of mu is just equal to negative g prime of mu, which is equal to 0. And that gives us exactly what we want, right? So we do this trick with proofs a lot. Usually there's one case that's much harder than the, or that takes much more work and intricacy. And then we say, okay, well, if it's a maximum, then when we consider the case of minima, just multiply by a negative. And, because we care about things equal to 0, it doesn't matter if you have a negative in front of it or not, because negative 0 is still 0. So, with this little trick, this little cheat allows us to not have to repeat all of the proof for the fact that you have a local minimum. You can just say, look, I did everything for the maximum, and boom, here it is. Okay, so let me show you a big, powerful theorem. This is called Rolle's theorem. It's one of those big, famous theorems in calculus. So let's give ourselves a little bit of extra room here. As I said, Rolle's theorem is a sort of stricter version of the mean value theorem, or you can think of the mean value theorem as a generalization of Rolle's theorem. So Rolle's theorem is really, really nice. It says, if f is a continuous function on a closed interval, and it's such that, well, at the endpoints of this thing, you're equal to 0, and f prime of x exists, at least, I'm going to put this in brackets, for all x in the open interval. So this would be the interior of that closed interval. See if you can use the definition to prove that. Then there exists some point in the middle or in between a and b such that the derivative has to be equal to 0. Okay, so before I do the proof, let me show you sort of the intuition here. So if I just sort of sketch out my function x, here, let me just draw, I don't know, maybe something like that. I apologize for the sort of squiggliness. Let's say this is A, this is B, essentially what this is saying is if you traverse the function f of x, well, the sort of displacement where you started and where you ended is equal. You started and ended at exactly the same spot, and that's 0. So that means somewhere in here, let's put this in blue, you had to turn around. So somewhere in here, you have a point where your derivative has to be 0. That's all this is saying, is just that you had to turn around, and we know that the turnaround points are local extrema, and therefore from the previous theorem, we know that that's where the derivative is equal to 0. So how do we do the proof? Well, it's mostly just what I said here. So first of all, let's rule out an obvious case. If f is identically 0, so it's just the 0 function, right? The 0 vector, well, then the theorem is trivial. Then the theorem is automatically true. And the reason for that is because it's a constant function, and therefore its derivative is equal to 0. And so, you can pick any mu in between a and b, and the theorem is solved. So now let's say if there exists some x0 in a and b, such that f is positive at x0. So you eventually get off of the x-axis. This thing can't just be identically the 0 function. Then the maximum point, right? So you eventually have to hit some maximum because you're a continuous function and you're positive. So the extreme value theorem tells you that there's a supremum here, and you achieve it. The maximum point of f on AB occurs at some mu in between A and B. It's in the interior. But then this tells you from the previous theorem that we have f prime of mu is equal to 0 by the previous theorem. And that is because the open interval is the interior of the closed interval, right? There's wiggle room for the open interval. No matter where mu is in there, it's an interior point. I can move around, I can wiggle around inside that. And that just comes from the fact that the open interval is an open set, right? We talked about this early on. So alternatively, if there exists an x0 such that you're negative, right? So we have to think about the other case. Maybe your function is negative. Then again, the minimum point of f occurs for some mu in AB, and the same argument applies. So just like what we saw with the previous theorem, right? It's the maximum that requires a little bit of work. The minimum case is identical, essentially. So this tells us Rolle's theorem essentially comes as a sort of corollary of our first theorem that we proved here about the derivative being 0 when you have a max or a min. Okay, so let's generalize Rolle's theorem, and let's generalize it to the mean value theorem, right? The name of the lecture, one of the big 3 calculus theorems, at least introductory calculus theorems, one of the most famous theorems in all of calculus, very, very important. And it comes up in sort of weird places. We're going to see it in the next lecture, talking about the fundamental theorem of calculus and how the mean value theorem can help us there. And what we're going to do after we prove the mean value theorem is show like all kinds of little results that you can derive about functions just using the mean value theorem. Okay, so the first thing is, what does the mean value theorem say? Well, suppose that you have a continuous function on a closed interval and differentiable on, again, at least the open part of it, the interior of this thing. So derivatives exist at every point except maybe the endpoints. Well, then there exists some mu in the interior such that the derivative of f at mu is equal to f of b minus f of a divided by b minus a. Okay, so what the heck does that even say, right? Well, you should read the right-hand side of this, f of b minus f of a, that's the rise. B minus a is the run. So what this is giving you is a slope, and it says the slope of the secant line that connects this point, a comma f of a, to b comma f of b. Well, there is a slope of the tangent along this function f that is the same as the slope of the secant line to this function. Now, why is Rolle's theorem an immediate corollary of this? Well, if f of b is equal to f of a, the right-hand side here is equal to 0, which tells us from the mean value theorem that there's a point where the derivative is equal to 0. So Rolle's theorem immediately comes from the mean value theorem, even though I proved it in a completely different way, right? Okay, so how do we prove the mean value theorem? Well, the proof is really, really fun, in my opinion. So first of all, observe that the secant line, sometimes we call this, secant. Sometimes we call this a chord if you're coming at this from a sort of geometric perspective, but I'm going to use secant line. The secant line joining this point, a comma f of a, to b comma f of b. Well, this thing is described by the line, well, let's call it y, and this is going to have f of a plus, so I'm not going to put it in y equals mx plus b form. I'm going to write it like this so that you can easily check that indeed when you put in, say, x equal to a to this thing, you get f of a, and when you put in x equal to b to this thing, you get f of b. Okay, so I write it like that so you can easily see what the slope is, and you can easily see that it actually connects the two endpoints. So now, for all x between a and b, let's define, let's say h of x is equal to my original function f of x minus the line that I described above, okay? So really this is f of x minus f of a minus, and then this slope term divided by b minus a. So don't be intimidated by all of the sort of symbols in there. There's really only x dependence. Let's underline the x dependent terms. 1, 2. There's only 2 x dependent terms. The rest of it is just a bunch of junky constants. Okay. So then this thing represents the height between the graph f and the graph of the secant. So we're going to ask ourselves when the derivative of this thing is equal to 0. So first note, well, h is a continuous function on AB. This comes from the fact that f is continuous and a linear function, a line, it's a polynomial, and therefore it also is continuous. So if you subtract 2 continuous functions, still continuous, right? We did all this work, we might as well use it. And h of a is equal to 0, which is equal to h of b, right? So that's just sort of by design. Again, h is measuring the difference from the line to the function, and we know that these things align by the definition of the line at the endpoints. Also, h prime exists for all x in AB. So, by Rolle's theorem, there exists a mu in between A and B such that h prime of mu is equal to 0. Now we know the derivative is equal to 0. Let's actually take the derivative here. This implies that, so the derivative of h, I just scrolled away from it, but this is f prime of x minus f of b minus f of a divided by b minus a. That's the derivative of the line. That's just the slope. This is equal to 0, which clearly tells us, sorry, there should be a mu here, which tells us that we have the mean value theorem, right? Because this tells us the slope of the tangent at mu is equal to the slope of that line that I defined, thus giving me my nice mean value theorem result. And one of the things that used to frustrate me as an undergraduate about the mean value theorem is people used to tell me all the time how important and how useful it was. And then I used to sort of look at the theorem and think to myself, sort of how, right? It doesn't look like it's really that important. So what I'm going to do for you is I'm going to give you a bunch of corollaries here. I'm going to give you 3 corollaries in a row that just boom, 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 all tell you properties about functions and are basically just the mean value theorem. But before that, let me do something. Let me show you how this connects to Taylor's theorem. Okay, so let's rearrange the mean value theorem, MVT, to get, well, this is very similar to saying f of b is equal to f of a plus f prime of mu times b minus a. Okay, so what does that look like? Well, maybe if I replace the a with, or sorry, the b with an x here, that looks a lot like Taylor's theorem. And this is an even weaker version of Taylor's theorem than the differential that we saw in the previous, because this can be thought of as the Taylor remainder. I know that we haven't introduced Taylor's theorem yet, but I'm sort of operating on the assumption that many people have seen it already. If you haven't, that's okay. Keep this in the back of your mind. We're going to get there. But really, this is just a Taylor expansion up to just a constant, right? It's like the worst possible version of a Taylor expansion, because the remainder here is the linear term. And so you're sort of approximating your function by just a constant. It's a really, really weak version of the Taylor theorem, but nonetheless, it is a version of it. Okay, let me give you the corollaries. There's 3 of them in a row. If your derivative is identically 0 on an interval, say I, then f is constant on I. So if your derivative is 0, then your function, the only way this is possible is if your function is constant. Okay, so you know that this goes the other way too, right? The constant functions have 0 derivative. Now I'm saying, imagine I give you a function, I tell you its derivative is always 0, then that function had to have been constant. So let's say fix any a in my interval and let x and I be arbitrary. Okay, then the mean value theorem, again, MVT, implies that there exists a mu that is in this interval such that, well, if I'm using my mean value theorem, let's multiply up the denominator. So I get f of x minus f of a. This is equal to f prime of mu times x minus a. But my derivative, maybe I'll just put this in red underneath. This is equal to 0 everywhere in the interval. And so mu is in the interval. This is equal to 0, which tells me f of x is equal to f of a. But since x was arbitrary, this implies f is a constant function, because this works for any x that you pick. Boom. Mean value theorem gave us that one in one step. Let me show you another one. So let's look at another corollary here. if you have two functions, f prime and g prime, you know, two functions, their derivatives are equal everywhere on an interval. Then there exists some constant such that f of x is equal to g of x plus c. So this is actually the sort of MO for all of introductory integral calculus, right? When you're taking those integrals, you always have to add plus c on the end because the antiderivative is not unique. Well, that's exactly what this is telling you, right? If you know two derivatives are equal, then their antiderivatives, the original functions, they have to be differing by just a constant added to these functions. Okay, the proof here, really, really nice. It actually just uses the previous example or the previous corollary, which is just the mean value theorem. Let h of x equal to f of x minus g of x, and observe that h prime is identically 0 because the f and g have the same derivatives. And this is, of course, on the interval I. Then apply the previous corollary. To find h is constant. And so that means since h is constant, f and g just differ by a constant when you subtract them. And that means that f of x can be written as g of x plus some constant. Right? Again, it's all of integral calculus. That's exactly how this works. Okay, here's a big one. And this is a lot of how you first learn derivatives when you're introduced to calculus, right? You probably learn things like the first derivative test, and you in particular learn that if your derivative is positive, you're increasing. If it's negative, you're decreasing. Well, this again just comes from the mean value theorem. So let me put this huge corollary in here. Suppose f is a continuous function on a closed interval. And this thing is differentiable, again, at least on the interior, on AB. So we don't really talk about the endpoints when we talk about differentiability because the limit as h goes to 0 can only work in one direction. So that's why we typically restrict ourselves to just the interior here. Okay, bear with me. We've got a lot of writing here. If f prime of x is greater than or equal to 0 for all x in this interval, then f is increasing. So we've already introduced the definition of increasing. So I'm not going to hash that back out, but it's a fairly intuitive definition. 2, clearly, if f prime of x is strictly increasing for all x in AB, then f is strictly increasing. On AB. Now I'm going to do decreasing. I'm going to write it. You could probably interpolate. You might even want to fast forward through this. It's just more writing than it is thinking again. But if f prime is less than or equal to 0 for all x in AB, then f is decreasing on AB. And I thought about being lazy and not writing it, but that's not a good practice here. And let's actually write it. So if f prime of x is less than 0 for all x in AB, then f is strictly decreasing on AB. So again, you may need to remind yourself what it means to be increasing and decreasing, and in particular, strictly increasing, strictly decreasing. Go back, check those definitions when we started talking about functions, and in particular, continuous functions. But it's, again, it's fairly intuitive, right? Especially if you sort of draw the picture here. And now we have a deep connection with derivatives, at least when you can take a derivative of the function. Let me show you the proof. I promised you this was going to be a consequence of the mean value theorem. So let me show you how it works. I'm only going to prove part one here because everything else is identical. Okay, so after you prove one, they're all exactly the same. Let's just do one. So suppose f prime of x is greater than or equal to 0 for all x in AB, open. So then if x1 is less than x2, and these things are points in the interval AB, closed, the mean value theorem, MVT, implies that there exists some mu in AB such that, well, again, it's just the mean value theorem, nothing fancy. This is equal to f prime of mu times x2 minus x1. Let me just scribble underneath. This thing is greater than 0. This thing is greater than or equal to 0. And so therefore, this is greater than or equal to 0, which implies that f of x2 is greater than or equal to f of x1, which implies f is increasing. Right? And that comes from the fact that x1 is less than x2. That means that you sort of have this order preserved in the range of the function. And every single other one is identical to that. Okay, so how do you use this in practice, right? How could this be of benefit to me? Well, one thing that this is really, really nice for is showing that maybe one function is bigger than another function. So let me say, if I have a positive x, then I want to be able to prove that sine of x is less than x. Okay, so we haven't actually proven that the derivative of sine of x is cos of x, but we can take that for granted. This is something that is usually introduced in introductory calculus classes, so we can take that for granted. Okay, so what's the proof here? Well, we're going to show that a certain function is increasing, and therefore, we have exactly what we need. So let me show you how this argument goes. Let's say let f of x equal to x minus sine of x. Okay, well, first of all, then f of 0 is equal to 0, and f prime of x is 1 minus cos of x. And notice, now again, I'm using some properties of cosine of x. We haven't proven them in this class, but that's okay. You can take them for granted. You spent a lot of time working with trigonometric functions, probably. You're allowed to, use your knowledge here, right? I'm not trying to wall off anything. We're just trying to prove things from first principles. Well, then f prime of x is strictly greater than 0 for all x between 0 and 2 pi. Notice that I'm excluding 0 and 2 pi. Those are the points where cos is equal to 1. So this is actually a strict inequality. And by the previous inequality, or by the previous corollary, this implies f is strictly increasing on the closed interval 0 to 2 pi. Remember, the corollary gave us that if you're increasing, or if the inequality for the derivative holds on the open interval, then you're increasing or decreasing on the closed interval. So I can close it off here. And this tells me so that f of x is bigger than f of 0, which is equal to 0 for all x in, let's say, 0 to 2 pi inclusive. So if I lock out 0 there, hence, well, since f is positive, this tells me that x is bigger than sine of x for all x in 0 to 2 pi inclusive. But there's a lot more x's to consider, right? What if x is bigger than 2 pi? But since 2 pi is bigger than 1, right? It's like 6.28 whatever. Then x bigger than 2 pi is bigger than 1, which is bigger than or equal to sine of x, which implies x is bigger than sine of x when x is bigger than 2 pi as well. And therefore, really, the heavy lifting of this was done by the previous corollary, because we really just had to care about between 0 and 2 pi. Okay, let's round off this lecture with two little definitions, and then we'll talk about a simple application of them and in a little example, and that'll be it for this one, right? Because I know that I've sort of bombarded you with a lot of little mini results and a lot of definitions in this one. But again, I kind of hope that most of what you've seen today is probably review. The interesting part is how we do the proofs, how you apply the definitions to obtain the results. All right, let's look at a definition. A function f, which transports you from an interval I into the real numbers, so where I is an interval, is called monotone on I, if and only if f is either increasing or decreasing throughout I. So this is basically the natural extension of a monotone sequence to a monotone function, right? If you go back and compare what it means for a sequence to be increasing or decreasing and where we got monotone from, then the same thing happens here, right? For a function, it's just a natural extension of this. And the function f is strictly monotone, so nothing probably too new here. Strictly monotone, provided it is either strictly increasing or strictly decreasing throughout I. So I'll just put strictly here. Okay, nothing too exciting. Let's do one last definition for you. Well, this one is one-to-one, right? Or injective. So a function f, again, from a domain into R. So it doesn't have to be an interval this time. It's just a domain. So where D is contained in R, could be the whole real numbers. Well, this is called injective if and only if f is 1 to 1. Now, what does it mean to be 1 to 1? Well, i.e., that means that f of x1 is equal to f of x2 if and only if x1 was equal to x2. So it basically tells you you get a unique value in the range for every single element of the domain that you put into this thing, right? The only way you get the same value in the range is if you put in the same values. So examples of one-to-one functions are, f of x equal to x over the real numbers. Functions that are not one-to-one would be f of x equal to x squared, right? Because that bend, the parabola bend, tells us, say, for example, there's two values of the domain that give you 4 in the range, right? Plus or minus 2 both give you the same value. And so you're not injective, you're not one-to-one. All right, let me leave you with the final example here, right? So a function f that is strictly monotone on an interval I must be injective on I. Right, so strictly monotone means strictly increasing or decreasing. That means that you can never repeat the same value in the range as you sweep over the interval I. And since you can never repeat the same value in the range, that means that you must have an injective function. Okay, so we had a lot of fun, right? We got to see some very, very important theorems from single variable calculus, Rolle's theorem and its generalization, the mean value theorem. Now, just like I was emphasizing in the previous video, the mean value theorem has a strong connection to Taylor's theorem, which we are slowly sort of building ourselves up to. Now, the other nice thing about the mean value theorem is it's going to be crucial in proving the fundamental theorem of calculus, which is one, it's the fundamental theorem. It's one of the most important theorems in all of calculus. And if you recall, I'm going to show you what it is, but it tells you it relates integrals and derivatives. It says that they are sort of undoing each other. So we're going to get there as we progress through, but what we got to do today was lay the foundation for it, and in particular, understand really what the derivative tells us about a function in terms of increasing or decreasing, or if it's turning around at a local extreme point.